In this video, we will try to get an idea about of work done by a variable force. Right? Earlier, when we discussed work done, we had this equation: work done is equal to force into displacement. Say, for example, we have a surface on which we have a block of wood, right? And when we apply a force F, this block moves through a small distance or some distance s. Let us say this is the distance it has moved through s. And the product of this force applied and the distance or the displacement give us work done. When we use this formula, the underlying assumption was the force applied is constant throughout the displacement. That is, when this block moved from this location to this location throughout the displacement, the force is constant. That was an assumption which was made. In reality, that is rarely the case. That means forces are generally not very constant, right? Forces keep on changing, right? And there are a large number of examples that can be given of. Let us take an example which we of course don't see on a day-to-day basis, but I'm sure you will be able to connect to. Let us say we are firing a rocket from the surface of the earth. Let us say this is the surface of the earth and a rocket is being fired from the surface of the earth. Initially, the force of gravity which is keeping this rocket on the surface of the earth is g m1 m2 r square, where m1 m2 are the masses of the earth and the rocket, and r is the distance between the rocket and the earth. Since the distance r is very small, the force is extremely high, and therefore a large amount of energy is to be given so that the force that required to keep it moving away from the earth is sufficient enough to overcome this force of attraction, right? But as it keeps on going up into there, when it reaches this particular location, the distance r has increased. So this value increases, right? And therefore F decreases. Therefore, the force which is required to keep it moving away from the earth keeps on decreasing as it goes away from the earth. So while the rocket is going through this displacement, the force acting on it is keeping on changing, keeps on decreasing. That means it's a variable force. This is a good example of a variable force. And now let us try to understand how do we find out, or how do we get an equation to calculate the work done by a variable force. Coming back to work done when the force is constant, if you plot a graph of F versus displacement, you'll get a straight line because force is constant. But in this particular case, when force is variable, we get a curve. Right? This is force and this is displacement S. Curve, because the force is not constant, it is variable. Right? The curve may be going down, the curve may be going up, right? But certainly it would not be a straight line. Now, if you want to calculate the work done in this case, that would be given by the area below this graph, because in this case, as we saw over here, the area below the graph is the product of force and displacement. Similarly, area below this particular graph will give us the work done. To calculate the area, what we'll do is we'll take an extremely small strip of delta S. Right? Now, this width being extremely small, the value of force practically remains constant. There's a very small change in force which we can neglect, and therefore force can be practically considered constant, and therefore the work done for this particular small strip would be delta W. Very small work done would be F into delta S. F is constant. And if I take up such small strips throughout, the total work done would be sigma of F delta S. So if I keep on adding these particular strips, and I'll get the total area below the graph, and I'll be able to find out the work done. Now if we take delta S tending towards 0, if we take delta S very small, right, means an extremely small thin strip, infinitesimally small thin strip, delta S is tending towards 0. In that case, what would happen is, as the displacement approaches 0, as this S approaches 0, then the number of terms in the number of terms over here, right, would increase towards infinity. Right? There would be infinite terms of F delta S, because delta S is very small, so there would be infinite number of small strips and therefore infinite number of terms in this, and the sum, the sigma, the sum would approach a definite value which would be equal to area under the curve. Right? And in that case, we would rewrite this as limit of delta S tends to 0 F delta S. Right? And in integral, in calculus, we would write this as work done is equal to integration of f delta s from s1 to s2, where s1 s2 are the limits, where s1 is this particular value of and the last is s2. So between limits s1 and s2, f delta s would give us the total work done. And the mathematical value, if I calculate this, it will come out to be the area below the graph, which would be equal to the total work done. Therefore, we write down as work done by a variable force is equal to area under the force curve and the displacement axis. Right? Force curve, this is the force curve, right? And this is the displacement axis. The area below this total area, this would give me the work done. So this is how we look at work done when the force is variable. We use calculus, we use integration so that we get the summation, the addition of extremely small thin strips, and for each and every strip the force is nearly constant, and when we add these small strips we would get the work done. Right? Thank you.